Hello there and welcome to Lower 6 Maths A-Level. This is the Applied Practice Paper H, and here we're working on question 4, a hypothesis testing question. A company claims that a quarter of bolts sent to them are faulty. To test this claim, the number of faulty bolts in a random sample of 50 is recorded. Give two reasons why binomial distribution may be suitable for the number of faulty bolts in the sample. Okay, so a number of reasons here. What we need is for each bolt to either be faulty or not faulty, two clear options there. The probability of being faulty or not may be assumed to be constant throughout the batches of bolts that they get, and one bolt being faulty does not affect another bolt being faulty. So for example, bolts don't come in batches of faulty, higher probability of faultiness. And we have a clear defined number of trials here, 50, of what we're going to test for being faulty and not faulty. And we've got a random sample here. Okay, so I'm going to move on to part B now, using a 5% significance level with the model of binomial distribution. Find the critical region for a two-tailed test of hypothesis test that the probability of a bolt being faulty is 0.25. Okay, so let's imagine a scale of probability where we have down from 0% to 100%. Now what we're looking for here is for a bolt to be faulty or not faulty, and we're going to assume to start with that it has a probability of 0.25. So you would expect out of 50 bolts for about 12 to 13 of them to be faulty. And if maybe only 8 were faulty, or maybe as high as 15 bolts were faulty, maybe there's some leeway that we could allow there. So what we want is the maximum amount of leeway that we're going to allow such that 2.5% and below, anything with a probability below 2.5% of happening, then we're going to discount that and assume our probability of faultiness is different. Or if we have something with a greater than 97.5% probability, we're going to assume here that maybe the probability of a bolt being faulty is more than 0.25. Okay, so what we want here is to find the exact number at which the probability of, let's call this x1 here and this x2 here. For x1, this is the number of bolts that will give us a probability up to this amount that's less than 2.5. So in this case here, the probability up to this value of x1 is less than, or strictly less than 0.025. And we want to find this x1 value, or on the other end of the spectrum, the probability where x is less than or equal to x2 gives us such a high probability, 0.975, such that we would be suspicious of anything that came in above that. So for example, if 40 bolts came in as faulty out of the 50, we'd be suspicious that our probability was a little bit higher than 0.25. So what we need to do this is a cumulative probability distribution function, and handily we have this on our calculator. Select probability from your menu, scroll down once to get binomial cumulative distribution. What I suggest you do is use the list function and list some numbers down to about 25. I wouldn't expect more than 25 bolts to be faulty if we have a probability of 0.25. Select your assumed binomial distribution model, so 50 and 0.25. And what we need to do now is we need to look, now we're looking for this x1 to start with here. So is it 6 or is it 7? Well, 6 is going to give us a probability of 0.0195. So what we mean by that is if out of these 50 bolts that we're going to test, The probability where 6 or fewer of them are faulty is a probability of 0.0193. So about 1.9%. That's highly unlikely. If something like, if any number between 0 and 6 bolts came out to be faulty, that's really unlikely, and the probability of a faulty bolt would probably be lower. On the other end of the spectrum, keep on scrolling down in your calculator, and now we're looking for a probability that's just over 0.975. So in this case here, the probability where x is less than or equal to, in this case we're going to have to go with, it's nearly 18, it's not quite 18, we're going to have to go with 19 here. The probability of get out of these 50 bolts, getting less than 19 of them to fail is really likely. You're probably going to get a number that's of bolts that is less than or equal to 19 that are going to fail. So that means on the other end of that spectrum, the probability of a bolt failing, of more than 20 bolts failing, is really low. That's 0.014. So 1.4% chance that 20 or more bolts are going to be faulty out of this model here. So what we're going to say here is our critical region where we suspect that the probability is going to be different from 0.25 is within the region x is less than or equal to 6, or this is a U-shaped symbol here, or x is greater than or equal to 20. Now that's saying anything in between 7 to 19, there is a more than likely probability that the probability of a bolt being faulty is 0.25. And I wouldn't be suspicious if out of these 50 bolts, between 7 to 19 failures happened. I would, however, be suspicious if 6 or fewer bolts failed that test out of 50, or 20 or more bolts failed that test out of 50. In this case here, the x is less than or equal to 6, I would suggest that maybe the probability is less than 0.25. And in this case here, where the x number is more than or equal to 20, that our probability of 0.25 will be more than that, because we've got so many failures here. So our critical region here, this is what we're looking for. The probability of find the critical region for a two-tailed test that a hypothesis of a bolt being faulty is 0.25. This is our answer here. X is less than or equal to 6, because that gives us a probability of less than 2.5%, and x is greater than or equal to 20, because this gives us a probability of less than 2.5% as well. Combine that and you get a 5% significance level test. Okay, so do keep this probability distribution function on your calculator usable to you, or keep on reminding yourself that it's here by doing these sorts of questions, because it's really useful when it comes to comparing probabilities to make sure that you've got a probability that's over 97.5% or under 2.5%. Okay, that's 6 marks for that question.